Hi everyone. Last seminar of term with Martin today, and he's going to be talking about models of physical networks. We had a lot of technical issues, but everything is working now, so I hope the talk goes completely well. If you have about 40 minutes to speak. Okay. Yeah. Okay, so thank you. I think stuff. Yeah, so I'm Martin Posfai. I come from Central European University, the university who gave up PhD offer to John Howe, who turned it down. Okay, so what I will talk about is physical networks, but I will start a little bit further away. So network science emerged from the early 2000s, and one of the big reasons for this is that data became available. So we had tons of network data coming from all these digital footprints and like emails being sent to each other, and so online social networks became slowly a thing. And this sparked a lot of discovery and interest in and perpetuated network science. But there was also some additional data available almost immediately, like that also sparked some research in temporal networks and spatial networks. And these past couple of years, we have an explosion in data where we have much more data available. But networks that are embedded in physical space, they're built from tangible objects. And we have this incredible experimental achievements. Like from the 2020, they made a detailed map of half of a fruit fly's brain. So you have the detailed structure of the neurons and the location of the synapses that has 25,000 neurons. And last year, they published a full brain that now has 150,000 neurons. But also there was this paper just looking at a very small sample from a mouse brain. But in addition to the structural data, they also have some measurements of the actual dynamics happening on top of it. So you have all this amazing data. This year, in February, there was this Nature paper on growing fungal networks where they grow this fungus in a petri dish, and they keep track of how it grows exactly. So you have dynamics of the networks growing itself, but you also have these increased other systems that are also networks, physical networks. You have these mechanical metamaterials. Metamaterials are like designed materials that are designed on a larger scale, so not on the atomic scale, but they build maybe nano or millimeter scale or centimeter scale objects, and they make materials out of that can have a complex network structure. But you also have experimental systems such as this like huge array of spin nano-Hall oscillators where magnetic field is spinning around, basically, and you have 100,000 of these oscillators that I'll talk about a little bit later on how you can organize these into complex networks. So you have all these experimental systems and empirical observations that are ripe for us to study in network science, because network science so far has not really focused on this. We simplified things down to just an abstract network or some small additional data. But having that said, graph theory has its origin in physical networks. So I borrowed this slide from Ilan Kuban from Netherlands. So the earliest use of graphs in the sciences goes back to chemistry and physics. So like the Cayley's tree counting theorem was to count the number of isomers you can have from a given set of atoms. But also the Hoya counting theorem is also something similar, or Florian in 1940s was doing random walks and networks, basically of graphs. And if you compare, like this is you can't really compare it because this isn't the way. So this figure up here is from Cayley's paper from 1874, and this is from Newman's paper in 2000. Kind of the underlying math didn't change. So there are very similar things going on. Only we forgot that we're coming from physical systems. Okay, so what do I call? I'll try to give some sort of definition for physical networks. Is a network where the nodes and links are actual physical objects embedded in three-dimensional space, such that they cannot overlap, or there's some other physical interaction between them. Some examples that you can think of. Neural networks are a very good example because they're really complex networks and we have a lot of data. But you can think of other biological networks or infrastructure networks that may fall into this category. And if you really want, you can think of road networks also as physical networks. So, and we're interested in how physical interactions such as volume exclusion or the cost of building these complex shapes would affect how they form, evolve, and function. So the usual stuff. in network science. Okay, but I can also give you a couple of bad examples of whether or not what things that we might not want to study. So example, power grid, the internet infrastructure, even the social networks are kind of made of physical objects. So they're physical objects. The power lines are physical objects, but they're too small. They don't really interact with each other that much in physical space. So these are better described as spatial networks. And spatial network description is having a list of connections, so having the combinatorial network plus the location of the nodes. And that information itself is enough for these systems so that we can answer a bunch of questions that are interesting for these systems. And because this data has been available for a long time, we have a big body of research that deals with spatial networks. So you can take any of the review papers or books by Mark Bartolome, and that gives you a good summary of what has been done. But basically, there are three questions that the comprehensive theory, or I divided up into three questions, we try to answer. So, like, how do we want to describe these systems? Because we don't only focus on the network structure, but also how it correlates with spatial structure. What are the right things to measure? And once you find these important common properties, how do you explain these? So for that, you would need generative simple models that also take into account spatial constraints. And finally, you're also interested in how does it affect the functioning of the system. So you might want to put some dynamics on these networks. And all these questions have been explored in the context of spatial networks. And we would like to do something similar in the context of physical networks, or at least contribute something to it. Okay, so as opposed to this, now the spatial network description, now for physical networks, we think that we need the list of connections. So again, a combinatorial network, but also the full shape and position orientation of these complex nodes that you can have. And this is a fairly, for us at least, it's a new thing to do in network science. So there are many open questions that you could pursue. But of course, network science is not the only science or field that is interested in these systems. There are many other related fields. For example, graph drawing in mathematics is like a classical thing that you can think of as a physical network is a planar graph, because things cannot overlap in a planar graph in 2D. In 3D, you can draw anything without an overlap, but there's a fair amount of research that goes into drawing 3D networks with some additional constraints, like adding a thickness to the links and constraining the total volume where you can put it into, or trying to draw them on grids themselves. Kolmogorov also did some foundational work, did some work on this in the 60s. That sparked my research. But the type of results that you have from this mathematical literature is kind of like give a bound on what is the minimum volume that you can draw a network with these constraints on it. So it's not really, you give it a network and then you try to draw it. You're not really trying to understand how these networks might emerge from real processes. Having that said, actually the motivation for this paper where they drew networks on a grid was actually the brain. So they say that the brain is following these volume constraints. So that's why it's interesting to study this. And then they give this abstract result related to that. But of course, polymer physics is very much related. The 40 self-avoiding random walks will also make use of these. For packing and percolation of 3D objects is again related. And study of specific physical networks, like neural networks, already in the late 19th century, you had these images drawn by hand of neurons. These are very big neurons. They come from some sort of squid, and they were spread out and traced. That's how you have the shape. So there's a lot of work that we can build on. Okay, but then is there a way to? Okay, so we have this. The challenge that we face is that this is super complicated, right? And if you look at this, maybe you can measure some things on it, but you wouldn't really know what is there for a reason, for biological reasons, what is a physical constraint, or how a network like this should look like, or should we compare it to? So this is why we want to have very simple tractable models that are minimal models of physical networks. So that I'm going to lose all this complexity. So what is the most simple model that is useful for network science? Well, the Adler-Shinnik model is a good candidate because you just have n nodes and links you sprinkle on top of them, and that's it. But this already has many interesting properties. It has this, and you can still be studied. There are new things there, but then everybody knows that there's a percolation transition in there. This is very much not like reality, but why we're interested in this in network science, because it's a good null model to compare to. It's also gives us an idea on what we should be looking for. For example, this percolation transition was also described by Adush and Laney, but then this gave the background for studying percolation as a measure of robustness in complex networks. It also gives us an idea of what the mathematics should be that we could use to describe more complex models, right? So the generating function formalism is connected to this, and that could be used to more complex models. So what is the possible generalization of the error model to physical networks? One possibility is, again, we just sprinkle m nodes in space and we start connecting them pairwise in random order. But now we give a diameter to the links, and if we add a link but it overlaps with an existing link, we just reject it. Okay? And this is a generalization because if you set the diameter to be 0, then of course you get the average model. But one complaint could be that the average model, the links are approximately statistically independent from each other. This is not the case over here, but I think if you want to include physicality, you have to lose this independence because the links have to interact with each other. Otherwise, they're not going to be physical. Okay, so what are things that we can measure in this system? What this is that it shows you on the horizontal axis, you have the number of links that we have deposited successfully. And on the vertical axis, you have the average link length in the system so far. And this is for the different colors are for different diameters. So if you have very thin links, then the expected length of the links will stay the same, meaning that we don't really reject links. And basically this value is going to be the expected length of randomly picking a segment from a unit cube. But if you have more thick diameters, then physicality starts to kick in at some point, and you start to deviate from this line, and the links that you add are going to be shorter and shorter. And eventually you can't add anything anymore because you run out of options that are valid. Okay, so there are the two kind of interesting transitions or points that we could be interested in. When does physicality start to matter? And when do things get saturated where we cannot add anything to the system anymore? Yes.
So you put the saturation, you write with singularity. If you don't add anything after 1,000 steps.
The thing is, this is like a nuance compared to packing.
Yeah.
It's different because we're in real space, but then the endpoints are chosen ahead of time. We have n endpoints, so we can't have n square possible links.
Okay.
So if we run out of possibilities, then we're done.
Okay.
Right? For regular random sequential deposition, you have this problem that you have continuum many places that you could place it, and you don't really know when you're done.
Okay,
But
you can.
you can, and this is a huge simplification too. Yeah.
So here you've optimized for each line, for each lambda, you've optimized how many you can put in.
No, we did not optimize. This is random deposition. Random.
Nice. So you stop when you evaluate all the other possibilities
Yes.
and none of them
Yes.
can be placed.
Yes. But if we would do it in a more smart order, then of course we could place more. But this is the random version. Yeah.
Sorry, can I ask?
Yes.
How much sort of deviation do we see in MMAX? If it has a really bad strategy for placing them versus a really good.
So because this is random, it concentrates on a value.
Okay.
So you can calculate also the standard deviation, and it goes there, and also you can do those calculations. There's some math literature on doing. I can circle back a little bit. Yes.
Sorry if I'm confusing you, George said it, but is MMAX here the expectation of MMAX, or is it the maximum?
This is just measurement, so it's an ensemble average.
Okay.
It's like 50, 100 simulations, the average of that. Okay, so the way that you can approach characterizing this is that we introduce an auxiliary graph that would capture the conflicts between the edge candidates that you can. So this is your original physical network over here, and then the auxiliary graph that we call metagraph for some reason has vertices that correspond to edge candidates. So you have now n squared over 2 vertices in this, and if 2 edge candidates overlap with each other, we add an edge between them and over here indicating that these 2 cannot be added at the same time. And the connection is kind of clear. So here's a metagraph corresponding to, I think, exactly this system. And a physical network in the system would correspond to an independent set in this metagraph. And an independent set is a set of vertices that do not share or are not connected to each other. Right? And the construction that we have is going to be this randomized greedy construction of an independent set that had been studied for configuration model. For example, it's proven to concentrate. But of course, this meta graph is not a configuration model, but we're going to kind of assume that it is. Okay, and then the thicker you are, the more dense the meta graph is, so the independent set becomes smaller and smaller. Okay, so these are the questions that we're going to answer. For this, we can try to characterize a little bit we want to do this in the large network limit. So how can we take the large network limit that is meaningful, right? If we fix the diameter of the edges, then we can't really take a large network limit because inside the unit cube, because it gets just too dense and everything overlaps. So we're going to estimate the number of the average degree of the meta graph. And then to do this, right, we have these segments that we drop on top of each other. So what is that? First, we ask what is the probability that you take two random segments in the unit cube and they overlap with each other? So I don't have sticks to demonstrate this well, but I took this from a textbook. And so this is the one such stuff, actually, that it was already present there, that you have these two sticks. Then the excluded volume of this stick would be that if we fix the angles, so when do these overlap? So on this axis over here, I could move it around except when it actually overlaps. And on this axis, it overlaps for proportional to the length. So the excluded volume is going to be lambda times the size of one of the rods and the size of the other rod. So approximately, that's the order of magnitude of the overlapping volume. And then to get the average degree of the meta graph, typical length of random segments is just going to be the size of the cube. And we try to drop n square of these. The number of conflicts that you're going to generate is going to be proportional to lambda times n square. Okay, so now if we want to take, yes.
Have we made, I'm not sure I completely follow, but have we made an independence assumption somewhere along the way?
Yes, we did.
But we quite explicitly said that that's not the case. Right?
Yeah, so this is just going to be an estimate for it, because we don't take, and maybe I didn't say this, but we don't care about conflicts that are at a node. Because if we would care, then each node could only have one connection.
Right.
So at a node, you're allowed to overlap.
Yeah.
And then kind of the independence assumption works because these links are very long compared to how dense the nodes are.
Okay.
So you can approximate it as
But then when
the conflict between two links is going to be between two independent segments.
Yeah, not really.
Yeah.
Okay.
But this is just the scaling, and this could be checked numerically, and it's good. Works. So the way that we're going to take the infinite limit is that we're going to set the diameter to depend on the number of nodes that we have in the system as a power law. And the range for alpha that matters is that if alpha is too large, then the diameter shrinks too fast, and you have no conflicts. So, and the limit for this is 2. So of the meaningful range of alpha starts at 2. And if alpha is larger than 1/3, it doesn't shrink fast enough as we add the nodes to it, and it would fill up completely. So the alpha that we're interested in is going to be between 2 and 1/3. Okay, and then continuing with this, we're going to now, the metagraph itself is a too complicated object for us to deal with, so we're going to substitute with this mean field-like object. And so we're going to just say that we take the same number of edge candidates that we had before that have a length that we can measure or just draw from a distribution. That distribution is known, and we connect each two pair of the edge candidates with a probability that's going to be proportional to equal to this, which is the same as the probability if they would be independent from each other, right? So it would be randomly placed. So this way we get kind of a configuration model version of the metagraph that we can then use to do calculations. And I'm not going to go details because I think I already talked too much. Basically, you can do this degree biased calculation on mean field calculation on this randomized metagraph. And from that, you can get the total length of the links that you have deposited with scale with system size in the large network limit like this. And, you can extract these exponents out of the solution. Yes.
So what is the effect of the boundaries?
Effect of the boundaries. So that's it. We also did periodic boundaries, but now we have this card boundaries around it. And for these exponents, it doesn't really matter that much. the phenomenological reason for this is that as you add links and you get close to the saturation point, they start to shrink. And as they shrink, you don't really see the boundaries anymore that much. Initially, you do see them when the first ones you deposit, but the most of the edges that you are going to add are going to be short in the later stages, and then because of that, the scaling is not affected by that too much.
Do you explicitly keep track of nodes in this process, or is it just edges that are being deposited?
In the actual simulation, we keep track of the nodes.
I
So it's going to be an actual physical network that is real. In the analytics, no, it's just mean field type of business. Okay, so so this is a random sequential deposition, and we can get these analytical results out of it. And maybe it's interesting on why we can do this, because it's usually very hard. And the reason for this is that we kind of happen upon an easy problem that we're smart. So if you have a disk, is that a disk excluded volume of a disk is just going to be the disk itself plus some halo around it that is has the same radius as a disk. Right? So if you drop another disk within this excluded volume, like then they would overlap the two disks. So initially, when you start dropping these disks in an empty like square, then they don't overlap with each other if you only have a few. So the excluded volume is just going to be a linear function of the excluded volume of a single disk. But when they start overlapping each other, that's the region where you start rejecting disks. Then the size of the overlap, the area of the overlap over here, is going to be proportional to lambda squared, which is on the same order of magnitude as the disks themselves. So keeping track of the total excluded volume becomes a very difficult problem. And that's why it's just a super difficult problem to do anything analytically in these problems. In our case, we have these very elongated objects where the excluded volume of a single rod is going to be proportional to lambda. And when you start rejecting links, the overlap of the excluded volumes, so like there are cases where the excluded volume overlaps, but you don't reject them, right? So in case something like this. And then the area or the volume of the excluded volume is going to be smaller by an order of magnitude in lambda than the actual excluded volume. So you still have this additive property of the excluded volume, while you also have a non-trivial structure emerging out of it. And this kind of is right in the regime where we saturate in the saturation model. So that's why we can get out there. Yes.
I think I misunderstood the previous slide where you had a black circle, which was the actual thing that you're placing.
Yeah.
And then the orange halo around it.
Yes. So I don't have an actual overlap shown.
Yeah,
So
exactly.
the black circle would touch the orange.
Okay, so that's a violation.
That's
But the
a
black circle.
so the two black circles would touch. So
Exactly.
the center of the black circle would fall
Would be
into this.
this.
Yes.
So that's not an overlap in the system.
This is not an overlap. This is meant to demonstrate that you have an overlap of the excluded volumes. So the total excluded volume is not the sum of the two, but you have to subtract the overlap. Okay, but because of this, the only issue we have issues when the lambda or the alpha is 1/3. That's when you run into that issue of these things filling up, and you have to take into account the overlap. But the scaling doesn't really change. So actually, we can get because of this unfortunate situation, we can get these exponents on how these various things would scale, like the onset of physicality, the saturation point, and would scale with system size. And, maybe I could highlight a few things that might be interesting. So if alpha is larger than 1/3, then the saturated point is always going to be dense. So the average degree is going to be infinite. And the saturated point, or this line over here, in case of alpha 1/3 is when you get a sparse network in saturation. But the onset of physicality actually happens much earlier. So at alpha 1/3, it's like super sparse, not really in the sense of average degree. And physicality can also be seen. And the other thing maybe is that because of this weird relation, the actual occupied volume and the excluded volume is much larger, that you can have situations where this is the total volume of the system. And if alpha is larger than 1/3, then the total volume of the system, the occupied volume fraction of the cube is going to be 0. So it's very light in a way, but you can't see through it because they overlap with each other. Like you can't poke a stick through it, but the total volume is 0. Okay. So we also did a couple of other things, but I'm going to shift it because this is not maybe too far away from reality. So let me shift to another model that we did. If there, yes,
Something in relation to what was asked before. So if you were to first to give a priority initially to
Yeah.
the short ones,
yes,
to the long ones, how
it would
does
be
it change?
completely different. Yeah, you could place many more.
Okay.
More links. If you
You would
do the
expect
short
short
one,
change.
you would do something like lattice-like network, and then you can't add anything else in.
Yeah.
If you start with the long ones, I don't think it's going to change that much because we kind of do start with the long ones because there are many more long options than short ones.
Yeah.
Right. So if you could connect to your immediate spatial neighbor, you have n options and you have n squared long ones. So we kind of do that version anyway.
Okay.
So okay, so like maybe you can look at stuff like how does the degree distribution change, and actually you can have emergent preferential attachment happening because of these like shadowing effects and so on. So there are many interesting things that you can look at. But instead of that, I'm going to switch to a different model. So the network that we have just constructed is kind of like a traditional way to draw networks. So if you ask someone to draw a network, they're going to draw a circle and then lines connecting those circles. So in our case, they are spheres and the edges are extended connections. But for many real systems like a neuron, typically you would think of a neuron as a node and a synapse as a connection between them. So the node itself is huge and has this complex shape, but the link is a point-like connection between them. So you can do something like this, like trying to come up with a model where the nodes are extended objects and things are point-like connections. And the setup that we looked at is that you take a lattice. This is going to be the substrate that we're going to build our network in. And nodes are going to be subgraphs of this lattice. And two nodes can be connected if they are neighbors to each other on the lattice. Right? So very simple. In this case, we don't. All of them are just non-branching, just walks. But you could do more complicated things. And then you have this. This is going to be the full physical network that we want to describe, and this is the corresponding combinatorial. You can get out. So we wanted to do something again very simple that we can actually solve. And what we did is that we take a lattice and we start by a growing. We're going to define a growing model. We just start by selecting some subgraph that we call the first node. And then we pick a random point on the lattice and start a random walk. And we walk around until we hit the first node. And when we hit it, we're going to call this trajectory the second node in the system. And then we continue. The third node, again, we start a random walk from a random location until we hit the first or the second node, we do it. And then we can go on and we can build a network out of this. So in this case, it is going to be a tree that has a combinatorial network and a physical structure as well. But you can also do it in 3D, and you can do it in 4D and 5D. Just okay, so how should we grow a node? So a requirement, the idea is that these nodes should be growing fractal pieces. And a random walk is a good approach. But which random walk should we choose? What does mean? The natural choice could be self-avoiding random walk, as they use it as fully defined. So actually not as fully defined. The kinetic version of the self-avoiding random walk, which means that you just walk around. You can step in any direction, except if that site was already visited by you. Yes.
Sorry, you mentioned that it was a tree.
Yes.
Okay, I don't quite grasp the intuition as to why it needs to be a tree.
It's a tree because each time that you add a new node,
Yeah,
you start from a random point and you only connect it to the node that you hit. So there's only one connection. You could make it into a non-tree by adding additional connections or branching the walk or something like that.
I see.
But the simplest form is going to be a tree.
So do you choose the fixed destination but random starting?
Random starting point and any destination point that is already occupied by a physical node. Okay.
And can some of the lattice sites be occupied by more than one node?
No. But when you hit an existing node,
So that
that creates a link.
that's the link, but not
Yeah. Yeah. Okay. So these are random walks that avoid each other, but Flory studied it in an equilibrium setting. They said like all of the trajectories have the equal probability that have the same length. The kinetic version would be that you start from somewhere and you build it step by step, which is not the same. And in 2D, this gets stuck very easily, in 3D as well. So it kind of loops around itself and then it dies out. And one version to avoid this is that Yeah, okay, this just shows how you get stuck. And you get stuck in 2D instead of approximately 70 steps. So these are known results. This is also a known thing. So people introduced the Laplacian random walks to study polymers and like this kinetic version of polymers. And the idea here is that you when you do the random walk between each steps, you have to solve the Laplace equation in a way that the boundary conditions are that the outside of the box will be 1, and the walk itself will have 0 value, and then you solve the Laplace equation to get the intermediate points. And then the probability of making your next step from here, you choose the probability depending on this field. And in a way that is going to be this field to the power of A. So why is this good? Why is this self-avoiding? It's self-avoiding because phi is set to be 0 for the walk itself, so we would never step there. The probability of that is 0. But why it doesn't get trapped? Well, it doesn't get trapped because before you would get trapped, you do this walk around, and now if I would step here, it would be trapped. But at this point, it's completely surrounded by 0 as a boundary condition. So the inside will also be 0 automatically. And so that's 0 over there, so you can't step inside. But this is not what we do. This is overcomplicated. This is too hard to simulate, but I didn't want to. What actually an equivalent random walk for the A exponent equals 0 case is a very nice random walk. It's the loop erased random walk. That you you do a random walk, you step on yourself, and at this point you delete the loop that you have created and go on. And this has many nice properties. It can be analytically solved for 2D. For example, the fractal dimension of this is known exactly. And the other very nice connection is that, maybe I can get back to it later, but if you do this loop erased random walk on a graph and you do the construction that we did, then you get a spanning tree in the end, right? So if you forget the labels, you get a spanning tree. And that spanning tree with loop erased random walk is a uniform spanning tree of the system. So the Wilson theorem.
Uniform, you sample the
All possible spanning trees, and it's going to be a uniform sample. Okay, so what is that now? What we're going to be interested in. But you can also do like the mean field version of it. Again, the super simple version of it would be that you don't really do a random walk, but you allow disconnected points. So you just randomly pick points and until you overlap with something interesting. And now if you do a construction like this, you can always see that you get something degree heterogeneous out of it, as you might expect. As the early nodes added at early times, they would have higher degree because they're going to be larger. Okay, so to solve actually something analytically about this model, the first ingredient that we would need is what is the probability that we have two like random fractal pieces that we place in the unit or the lattice that we have? What is it that they're going to, probably that they overlap with each other? So let's say you have two different size random pieces. And okay, if they're random jumps, and so the mean field version is kind of simple. It's going to be proportional to the volume of one of the blocks, the volume of the other node, divided by the lattice itself. And so this is true, of course, if these sizes are small compared to the entire lattice. It's a small one. But for the fractal pieces, we can still work it out. So here's your entire lattice over here, and we have two fractal pieces with linear size L1 and L2. First we tile the entire lattice with L2 boxes. So this is the size of the small part. And this here is the size of the larger piece, the linear size. So it's inside here somewhere. It doesn't fill it up completely because it's a fractal. So in order for the two pieces to overlap with each other, what you need is that the small one has to fall inside this bounding box over here first. The probability of that is going to be, I'm already running around this one. So the number of these smaller tiles that are inside the larger box is going to be L1 over L2 to the power of D. Right? It's just, there's no fractal here yet. Okay, but inside the large box, your large nodes, the large node is not present in every small box because it's a fractal. The number of small boxes that it's actually present in is L1 over L2 to the power of DF, the fractal dimension. And then when would they overlap? When they actually fall into the same small tile. And you can piece this together. So the probability that they overlap is going to be this expression over here that depends on the volume of the two nodes and the fractal dimension and the underlying dimension. If the fractal dimension itself is large enough, such that the twice the fractal dimension is larger than the underlying space, otherwise they completely avoid each other. And you get back to this mean field, which is exactly the same as the jumping around version of it. Okay, so why is this good for us? Because again, we can do this like independence assumptions and everything like that. And we can say that the idea is that you grow until you hit something. So until the total probability of hit, if you have already t or t minus 1 fractal pieces, then hitting any one of those, if these probabilities are small, you can just sum them up. Right, so then it will be actually this expression over here, where this capital V is the total volume of all occupied nodes. Now, the main idea is that the new fractal walk or the fractal piece will grow until this probability becomes 1, as the sum of these probabilities is going to be approximately an order of magnitude of 1. Because if it's much smaller, then they would just avoid and grow further. Right, so this is our kind of equation that we can build from. And from this, we can write down, like in a recursive way, we can write down the growth of the total volume of the system. Right, because this gives a relation between the size of the new fractal piece and the existing, all of them. And, this is something that you can solve and then extract again critical exponents out of it. So if you solve it, like this is for loop erased random walk, and you get a power law increase over time, where this t is the number of fractal pieces I have added so far. And as the total volume of the system grows with the predicted exponent for 2 and 3 and above dimension 3, you get the mean field exponent and nicely collapse with each other. And you can also then go ahead and push the network into saturation, again, filling up the entire lattice, and ask questions about this full system. Right? So you have this nice system that is self-similar, but also a space-filling type of thing. And you can calculate the degree volume correlations, see, but this is the size of the fractal pieces and their degree. And they have a linear relationship between them, which is maybe not surprising, but that's what you get. And the degree distribution that you get now will depend, it's going to be a power law, will depend on the fractal dimension of the system itself. Okay, so maybe this is kind of surprising. The reason is that normally to get a power law degree distribution, you need optimization or you need preferential attachment explicitly. And here we have this complete random growth. And the reason for this is twofold. One is that you have nodes are added sequentially, that means a lot. And then you have this externally limited node growth, that they are kind of self-regulating in a way that would result in a power. Okay, and for the loop erased random walks, you can actually do more. These results are really kind of hand wavy in a way, but some mathematicians that I work together with, they can prove some of the results, but for the special case of loop erased random walks, the fractal piece would work for other types of fractal pieces. Okay, so I'm going to have 5 10. Okay. I talked about structure, but I also promised to talk about how this structure would affect the dynamics of that. So, like, what can you do? You can then say, you go to the Laplacian of the network, is kind of a general approach would be that assumes that you have dynamics that depends on the difference between the node states on different nodes, and if you linearize around the fixed point, the matrix that you get over here is going to be the combinatorial Laplacian. This is for regular networks. We call it combinatorial because we're also going to do the physical version of it. Okay, so one main property of this is that there's always a trivial eigenvector that corresponds to a connected component that is equal to the eigenvalue of 0, and you have the trivial eigenvector correspond to the top ones. Right, so now we have this physical network set up. So our idea was that, okay, let's take this seriously and say that we can put a Laplacian on this entire system over here. So allow some diffusion to happen on the system. But let's say that inside the physical node, it's easy to diffuse, and between them, it's hard. So we're going to add a link weight over here, this W that goes to 0, or is very small. So if W is set to 0, then you get this disconnected pieces, like a block diagonal in the Laplacian, and all of these will have an individual trivial eigenvector. Now, if you turn on small, yes,
But this Laplacian, the nodes are the actual sort of the nodes in the physical network, or are they lattice points?
the lattice points.
I see. So these are not the same nodes as we talked about.
Yeah, these are lattice points, but we'll do a coarse graining. That is what we're doing right now. So if you turn on, make W very small, then what you get is, so the number of eigenvalues you have in the system is the number of lattice points that you are occupied. And you get this time scale separation in, over here is W, and you go to 0 this way, that you will have slow modes and will have fast modes. The fast modes kind of take the diffusion and spread them out inside the physical node very fast. But then from one physical node to the other, diffusion happens slowly, so you will have n slow eigenvalues. And you can do this coarse graining. It's actually exactly the same thing as people did for multi-layer or multiplex diffusion. But over there in multiplex diffusion, typically they had 1 or 2 layers that were of similar size. And over here, we have many, many layers that have very heterogeneous sizes. And this causes a difference. So this is what you get out of it. That you get for this coarse grain network. So naively, you might take just the Laplacian of the combinatorial network, but that's not good. You have to take that, plus you have to normalize by the volume of the individual nodes. Like we did the symmetric normalization here to make things easier to calculate, but it could be asymmetric. And this is also related to coarse graining and synchronization problems. So you get the same matrix out of there. Just over here, we have this extra interesting property that, okay, so this is in 5 or 3 to 7 minutes. I don't know, probably going to 2 minutes. So then this tells us that the interesting message, your take-home message, is obscured by Zoom. But the idea is that knowing the combinatorial network structure is not enough to study this type of diffusion, but you need some physical structure, but you don't need the whole. It's enough to know the volume of the nodes. So this is kind of nice because it gives you this complicated system, but it boils down to something manageable mathematical object, which is this node-weighted network that you have. Yes.
Just to clarify, does that result of node size is enough? Is it specifically for your null model, or is it for?
No,
is it specifically for the?
It's for any multi-layer network, say, or any modular network,
Yeah.
where you have weak connection between them. So if you look at those papers with the multi-layer diffusion, the only difference is that they don't have this explicit volume over there because the volumes were the same. But it's they have it's the same result.
The thing is that the mixing time inside each of the, because here you have the mixing time inside each of these nodes.
Yes, it could be very
Depends on the
different.
size, right?
So that's a very good question that we haven't mapped yet. So if you take W to go to very, very small, you can ensure that the largest node will also have enough mixing happening. But because it's a scale-free network, this is a good question that in reality, is this time scale, is it an achievable thing? So that's something that we are interested in understanding. Okay, but our result was that, an interesting result was that the degree of a node and its volume is linearly correlated with each other. So it means that these volumes that we plug in there are not going to be random independent of the combinatorial network, but they're kind of determined by each other. So there's a strong correlation, and that could have an effect on the dynamics. And the effect that you have is that if you have take the combinatorial network of our this is just a scale-free network. So the spectrum of the Laplacian will have the same power law decay as the degree distribution, and the leading eigenvalue is going to be equal to the degree of the node. It's going to be a localized eigenvector of that. So this is taking the green line shows the original, the combinatorial network. But if you normalize by the volume, it suppresses this tail completely, and you have a much faster decay. It's because the largest degree node is also divided by the largest volume. Yes.
Is the combinatorial graph still a tree?
Yeah.
So we're diffusing on a tree.
Yeah.
So we're just concentrating on the leaves, no? Somehow.
Uh,
You can come.
You can come back.
It's not nice, but.
Yeah.
yeah, standard. But these results don't matter. You can add more as long as you have a correlation between size and degree. The suppression it doesn't have to be a tree. The suppression happens. And okay, I'm not going into these details. If you randomize the volumes, of course, you don't get that suppression as you expect. Okay, and if you take the fruit fly brain and you look at the correlation, I mean, this is a jump because brain dynamics is not diffusion, whatnot. But there is a correlation between volume and degree, where the degree is number of synapses you have, and the volume is the actual volume of the neuron, or you can also take length of the neuron. So you can do it as an exercise. You can try calculate the Laplacian of the combinatorial network and this volume normalized version, and you get the same suppression. And you know, you can do it more systematic. You can look at other systems where maybe diffusion is more realistic dynamics, like porous media. You also have a correlation between the degree of a pore, a cavity, and the number of connections it has to neighboring pores. So there are other systems that you can study. And you can now do a systematic exploration without generating a physical network. You can just generate the network and assign a volume to it according to some power law. Maybe include some noise as well. And as an exercise, there are special cases. If alpha is 0, so everyone has the same volume, you get the combinatorial network. If the correlation is perfect, no noise, nothing, and alpha is 1, then you get the degree normalized Laplacian, which we know has a maximum of 2 for the spectral or the eigenvalue for bipartite networks. You need that for 2, but this also means that it has to, the suppression of the largest eigenvalue has to happen if there's a perfect correlation. And, we did this, or it's ongoing work. It's just a toy model where you take a random regular network and attach a hub to it. And we can look at the spectra, how it changes due to the attachment of the hub. And we also assign volumes to the hub and the random regular nodes. This is very similar to what Newman did in this paper where they looked at eigenvector centrality. It's the same setup, and you can use similar math compared to that. So if you just add something, then the combinatorial network kind of looks like you have a bulk corresponding to the random regular, so the Keston-McKay distribution, and you have an outlier eigenvalue corresponding to the maximum degree. And if now you change the volumes of these, so you start increasing the volume of the hub, then what you get is that this outlier eigenvalue starts to travel towards the bulk, and at some point it enters the bulk. And if you even go crazy and you make it very, very small compared to the other one, you can go out of the bulk on the other side. And the other thing that happens, you can look at the localization of the eigenvectors. Now in the Keston-McKay distribution, all the eigenvectors are completely delocalized if the degree is at least 3 in the random regular network. But the eigenvector for the hub is going to be localized. That's the starting point. But as you go and you travel inside the bulk, the kind of the degree suppresses, the volume suppresses the degree over here as well. And your corresponding eigenvector will become delocalized. And then it will become localized again when it becomes the feeder eigenvector, the other side. And so this could be analytically calculated for this simple model. Okay, you can get a phase diagram, and if you do this for more complicated networks, numerically, you can see the suppression of the largest eigenvalue for this is a scale-free network with artificially chosen volumes. And if you change alpha and you reach approximately 1, then you get the suppression of the largest eigenvalue, and you also get a localization transition happening in a window like this. And in the fruit library, what you get actually is that first the largest eigenvector is localized on the largest degree node over here. And when you turn on the volume suppression, you don't get a delocalized eigenvector because you have this huge noise happening. But you get a concentration on a different node over here that has the maximum degree to volume ratio. So it jumps a bit.
Just to understand that, so but this localization that people have been investigating for graph partitioning, for instance.
Mm-hmm.
So as far as I remember, localization tends to happen more on the leaves of the graph, right?
So there is a localization happening on that leaves.
On the high or on the low degree, because that's where.
So for graph partitioning, the leading eigenvector doesn't matter, right? Because
No,
it's the feeder.
The
feeder one matters.
I think that in the case of like very sparse, when the case of graphs that become very sparse,
Mhm.
as far as I remember, the intuition was that this localization would be induced by trajectories that go into branches and get stuck at the extremities of the branch. So you have a localization.
But that's not for the leading. I don't think that's for the leading.
I think it's for the leading.
Okay, but if you have a scale free degree distribution, it's very simple. It's just that you have the degree minus the adjacency.
Yes.
And just the degree is so large, that entry, that you can ignore everything else on that line. So you will convert at the degree as the degree of the maximum degree diverges, is that it becomes, you will have an eigenvector that is really just concentrated on that single node.
I think that maybe we talk of different localization, but the one that I think about is really something that is in a very sparse regime. What you have
So
is nothing to do with.
If you have a very sparse regime and you have many leaves, then the leaves themselves will always support, due to symmetry reasons, they will always support localized eigenvectors. Those will be localized on two nodes, right? Or it could be localized on two nodes. If you have a leaf, you could have +1, -1, and that's an eigenvector for the Laplacian. And that will always be localized this way. It doesn't matter. I can change anything in the system, that will always be localized that way. And we don't have that in our toy model because we chose random breakdown instead of Ladder-Shane for that reason. Okay, and then you can say that this is not the good dynamics for the brain, but we have this system that I mentioned before with the spin Hall nano-oscillators, and this experimentalist group led by Johanna Ackerman in Sweden. They build these arrays of oscillators, like 100,000 oscillators, and what we're trying to get them to do is to make a network of arrays with heterogeneous sizes, so that your combinatorial network underlying will be could be a scale-free network if you have large enough system going on. Of course, it will be a planar network with many additional correlations, and you can then tune the coupling constants and the parameters in the system that you can have this two-stage synchronization, where you can have, perhaps this is where the question that you had. So this. If there's Laplacian coupling between the oscillators, then it's if the mixing time is, so the coupling, we have to find that window so that the mixing time is at the largest node is also small enough compared to, or fast enough compared to the dynamics between them. So this is a question in this case, whether this will work. But maybe we can get into a state where all the clusters individually synchronize, and we can get a network out of it in sports grain sense, where this could be an application to this Laplacian. Yeah, and I think I will just generally stop here. This, I don't know how longer I went. No, I didn't. I was planning on not doing it right. Okay, so there are many open questions that you can look at, like other growth mechanisms that and the details of the growth. We have other papers that look at bundling, and Laszlo Barabashi has papers on entanglement happening on, and like exclusively having preferential attachment in the melodic system or configuration model embedded as a linear physical network. I'm also very interested in designing node volumes so that you can design the spectra of the Laplacian, getting up at the end. These are the people today I work together with. I got my funding through this big synergy grant most of the time, by these more famous Laszlos than I will ever, even if I change one thing to Laszlo. But these are the people I see that I work together with. So thank you.
You have to look at 15 minutes, but I have to stop the question. If we have questions.